Welcome back to the channel and to part 3 of our stupid simple small engine fuel injection project. I recommend that you watch part 1 and part 2 of this series in order to get up to speed because this is complicated stuff. So before I get started, I'm going to do a 30-second recap of the project so far. Our stupid simple system uses an Arduino just like the Speeduino NO2C, but we're ignoring all the rules and we're building a very simple system on purpose. Our original goal was to use one sensor, which is the MAP sensor, and in the previous episode, we proved that it was possible to run an engine on just one sensor. The engine ran great with and without a load, although there was some issues. This video series is intended to show the development process, and we have no problems showing our failures and our successes. Okay, that's the recap. Let's get started. Today, we're going to significantly improve the overall performance of the 212cc Predator engine by adding a second sensor. I know, that just doubled the complexity of the system, but I feel it's necessary. So, if you're keeping track, our stupid simple fuel injection system will now have a MAP sensor and a crankshaft sensor. So, right away I realized by having two sensors, then we might as well use Alpha N strategy. That makes sense, I get that. At some point in the future, we will try Alpha N, but today we're sticking with the MAP and the crank sensor, and we'll see where that takes us. Now in Season 6, Episode 3, we actually installed a crankshaft sensor on the engine for the simple high-powered adjustable ignition system upgrade. Since the crank sensor is already in place, we'll repurpose it for today's video. At the end of Episode 3, we simplified the circuit that drives the General Motors coil pack, and this is a verified and fully functional circuit. So once we get rid of the coil pack, we now have access to a very clean 5-volt square wave that we can directly connect to the Arduino. Over here we have an inductive proximity sensor operating on 12 volts, and when this guy detects the rotating metal bit on the crankshaft, it'll pass the 12 volts to here. This resistor and this resistor are the voltage dividers, and the 12 volts will get knocked down to 6 volts. Then I use a 5-volt Zener diode to clip the waveform so we have a perfect square wave with a voltage no more than 5 max. This circuit board is located here on the test bench. Now, since our test bench is not ideal and the wires connecting all this stuff are much longer than necessary, we're bound to get some noise before the signal gets to the Arduino, so we're going to be putting a 2.2K resistor here. Future Jimbo says this is necessary, so we're going to go with it. Now, technically I should add a little bit more filtering, but this will work for now. Now, due to time constraints, repurposing this crank sensor for today's video makes a lot of sense. This is a very clean signal, which is what I want for development purposes. Now, I could gin up a circuit to pull a signal from the magneto, but the magneto is an electrically noisy guy, and it may take a few days to come up with a circuit to filter the signal. Of course, if I have to order parts, it would take a lot longer, and I just don't have the time. I will definitely look into pulling the tax signal from the magneto, but for now we're going to be using the very clean signal we already have. It's all about time, and I really don't have extra time for quagmires. It's a YouTube thing. Okay, so it's very cold today, and tomorrow is going to be much nicer for setting this rig outside and doing some load testing. And that's fine because I have a lot of work I need to do right now. So first of all, the carburetor is temporarily back on the engine, and that'll make things a lot easier for development purposes. You see, I have to confirm that the crank signal is as clean as I claim it to be, and for that we need to look at the signal with an oscilloscope. Once I confirm we have a safe signal to work with, then I have to write the code for the Arduino to convert the crank signal into RPM data. It's better to do this with the carburetor installed because I'm going to have to rewrite all the software, and I don't want to have to spend hours debugging the EFI systems just so I can get data. In order to move forward, I have to take one step backwards. Hopefully that makes sense. Alright, let's fire this puppy up. Now on the oscilloscope, we're looking at the crank sensor signal, and basically this is a beautiful signal. But this is an old oscilloscope, and I really can't zoom in to inspect the edges of the signal, but to me it looks very nice. The scope is set to 5 volts per division, and I can see that we're just under 5 volts, and that's fine. I would rather be slightly under 5 volts than to be over 5 volts. So we definitely have a good crank signal, and now I can fiddle around with the software. Now, it may be possible to get our RPM data from the MAP sensor. You know, a lot of people suggested we look into this, so let's take a look at the MAP sensor on the oscilloscope. And boom, we're now looking at the MAP sensor signal. Let me pause this for a moment. So yeah, we get a signal that's proportional to the speed of the engine. Since we're looking at the pressure inside the intake manifold, this waveform is exactly 1/2 the speed of the crankshaft. So if we multiply the waves of this signal by 2, then that would translate to RPM. Now this dip here is the maximum vacuum where the intake valve is open and the engine's drawing in the air-fuel mixture. At idle with no load on the engine, this looks like a signal we could work with. However, if we were to put a load on the engine, this dip would get a lot smaller. The more of a load we put on the engine, the smaller this dip would get. So in order to use this signal, we would have to amplify it and then clip it. So yeah, it's definitely possible to use the MAP sensor for RPM. However, we would need to build a special circuit board to reshape the signal into a perfect 5-volt square wave, and that would give us reliable RPM data for when the engine's running with or without a load. Now since this dip is not consistent and it changes with the load, using software to analyze this raw signal and deriving RPM is probably possible, but it's a quagmire that would take a lot of time. Keep in mind, it takes 52 lines of code to convert the perfect square wave from the crank sensor into RPM data. Using this raw signal and letting the software figure it out is probably possible, but it would take some serious code to figure this out. It's probably better to amplify it and then clip it so we have a clean square wave signal that we can then process with basically the same code we're using for the crank sensor. If we were to keep the MAP sensor, then this is worth putting time and effort into. However, if we switch over to alpha end strategy, then we can ditch the MAP sensor and all we really need is throttle position and RPM. And for RPM, we can likely get that signal from the magneto, plus a bunch of doohickeys to clean up the signal so it's a nice square wave. Anyway, the bottom line is, yep, the MAP sensor can be used for RPM, but we're not going to pursue it right now. So off camera, I spent the day writing code to convert the crank sensor signal into RPM data. Since we know the crank sensor sends a clean signal, I ended up using a function generator to simulate the crank sensor. That way I didn't have to run the engine in the shop. So now the Arduino has additional data to do the very crude fuel calculations. As you can imagine, the software is starting to get very complex. But that's not a problem. I'm going to use ChatGTP to help integrate all the code, so we have a human and AI working together to quickly put together a workable solution for the engine management. Today, we're using AI as a tool in our toolbox. Fast forward 24 hours and I have really good news. Ladies and gentlemen, we have a simple but fully functional engine management system using only an Arduino and 2 sensors on the engine. As you can see, the throttle body fuel injection system is back on the engine. Now, as far as software goes, once I had all my ducks in a row, then I used this alternator to put a load on the engine, and the load was dialed in with this control panel. We covered how this system works in a previous episode that very few people watched. And that's too bad because this tool is absolutely necessary to tune EFI systems. The electrical load is dumped into a few heater elements in this trash can full of water. It works and it's cheap. Notice I didn't say meh. Some people complain when I say meh. Anyway, while the engine was running, I had to manually adjust the duty cycle of the fuel injector with this knob. Once the engine was happy with the amount of fuel at a certain RPM and at a certain load, I collected that data to build this simple fuel lookup table. It's a small table, but it gets the job done. Now the engine was tuned live, and I used some debug code that was spitting out of the serial port to adjust the values. The process was complex to say the least. When the engine's running, there's a lot of stuff going on and there's a lot of stuff to look at. So once I had a workable system, I converted this manual fuel control knob into a fuel trim knob, and then I went back through the entire lookup table and manually trimmed the fuel numbers for maximum power at various loads. This fuel table is as clean as it gets for a simple system. So at this point, the Arduino is in full control of the engine fueling, and this knob is now a tool for trimming the fuel bins. For normal operations, this knob will stay centered for zero trim. In the previous episode, we had very good results with just one sensor, but we did have idle issues. So this time around, we have RPM data to tell the Arduino we're at idle, which works out great. And since nothing really happens at idle as far as the engine doing real work, I went ahead and used maximum brute force to oversample the MAP sensor to get rock solid MAP sensor data. This brute force method at idle resulted in a perfect idle because the calculations were near perfect. We sampled a MAP sensor 3,500 times in order to find the true manifold pressure. If you recall, the MAP sensor signal looks like this. Now we want to know the value of the sensor right here. Unfortunately, the way the system works, reading the MAP sensor is completely random, and the signal completely changes while the engine's running. When I sample the sensor, we may sample here or here or here. So at idle, I use brute force to sample it 3,500 times. Eventually, I'll find the lowest value right here. Now, above 1600 RPM, I reduce the sample rate to 500 times, which is more than adequate. Now, due to the speed of the microprocessor, this brute force method is not an issue at all. So I know what some of you are thinking. Why not use the crank sensor to synchronize the reading of the MAP sensor? Yup, that would work, and with the crank sensor, we could get a reading here and here. We would get a reading here, which would not work, but that's no problem. We could throw that reading away and use this one with a little bit of code. That would definitely work. However, the goal is to possibly use the magneto as our source for RPM, and the magneto is not synchronized with the MAP sensor. So we would be back to square one and oversampling to get an accurate MAP sensor reading. You know, I reckon it's possible to mathematically find this point from the magneto pulse, but that's a lot of crazy timing code, and at the end of the day, 12 lines of brute force code is simple and it gets us the same thing, and performance of the engine doesn't suffer. I feel like this is more in line with stupid simple. Anyway, enough talk. Let me show you the end result of all this work. So now the system is completely automatic except for the fuel pump. I could use a relay to automate this, but today it's done by a switch. Once the fuel pump is on, we can then prime the system with this button. That gives the engine a shot of gasoline for easy starting. Next, we arm the system by flipping this switch. And now we're good to go. From this point forward, the Arduino is in full command. Right now, it's waiting for a valid crank signal, and once it sees that, the process of injecting fuel will magically begin. Let's fire this puppy up. So, not too shabby. The engine idles perfectly, and it will sit here all day with a rock solid idle. Now, putting a load on the engine at idle is perfectly acceptable, and that's because I'm using a lot of resources to ensure stability at low engine speeds. The normal Predator throttle works as expected because we left the governor intact. I can even manually goose the throttle with excellent engine response. Now there is a slight hiccup here because I forgot that the fuel table doesn't go past 4,000 RPM. You see, above 4,000 and we're out of range, and the engine's running on this last bin. Maybe that's a problem for future Jimbo. Click on the like button if this video series is worth continuing. Anyway, at more reasonable engine speeds, we have excellent throttle response. Okay, let's torture the engine and give the computer some real tough calculations. At idle, we're going to put a decent load on the engine. Now the way the load box works is a bit magical. At this low engine speed, the alternator can't generate enough power for a huge load, and we still get a decent load, but not enough to stall the engine. When I increase the engine speed, the load also increases. Right now, the load is just shy of stalling the engine, so this engine's working real hard. We can pretty much put the throttle on any position, and the Arduino has no problem calculating the fuel to keep the engine happy. This is pretty cool if I'm allowed to say that. However, the fuel injection behaves exactly like the original carburetor. So that's something that needs to be justified if you're looking to do a project like this. Now, we're doing throttle body fuel injection and we're using a hacked up carburetor for a throttle body. This works for a simple system, however, we are working on a port injector and something like this will squirt the fuel directly into the intake port. So there's a bit of math difference when doing port injection, but if we continue to stay ignorant to all the rules, I think we'll be okay. Now, obviously, I have some experience with fuel injection and I know what rules can be ignored for a stupid simple system. This works pretty damn good, and it's a good starting point for basic fuel injection. It's crude, but as you can see, on a small engine, crude seems to work just fine. Although, we did break a lot of established rules to get here. If breaking the rules is not your thing, and you want to learn what's really involved with electronic fuel injection, then the Arduino NO2C is probably the cheapest solution. And something like that will take you down a deep rabbit hole of what's really involved. If learning about complex systems is your thing, then there's a lot more out there that you can look at, for sure. Now, after the credits roll, I'll do a deeper dive into the process of how I did this in less than 24 hours. And I'll show you where the code is located if you want to have a look at it. But first, I think we need to shut this contraption off and let it cool down, then we can try a cold start. You know, just for fun. And I have no idea how this will behave when the engine's cold. Okay, it's been over an hour and the engine's at room temperature, so that's about as cold as it's gonna get. Now, if we have problems, I reckon we could twist the fuel trim knob to add fuel for warm up, or we can even bump the prime button to squirt extra fuel after the engine's running. My plan is to do nothing special and we'll just see what happens. Anyway, air-cooled engines warm up pretty quick, so there shouldn't be too much drama. Well, there was a slight hiccup for a moment, but somehow the Arduino reacted and kept the engine running. You know, there's no software for cold start, so I really don't know what happened. Interesting. So to shut off the engine, we could flip this switch and that would immediately stop the fuel injection. Or we can use the kill switch. This switch shuts the ignition off and has nothing to do with the fuel injection. Now, shutting off the ignition turns out to be not a problem. You see, when the Arduino detects that the engine's below 400 RPM, it'll automatically shut off the fuel injection. So there's really no possibility of flooding the engine. Now, if you missed part 1 and part 2, definitely watch them. This system absolutely doesn't work like you would expect it to. It's a continuous throttle body fuel injection, and there's no synchronization between the injector and anything else. The injector operates at a fixed frequency, which is 25 Hz, and the amount of fuel that gets injected is determined by the duty cycle of the injector. Now, the duty cycle is determined by the MAP sensor, plus a bunch of math. The crank sensor doesn't do anything other than let the Arduino know how fast the engine's spinning. The system is intentionally simple because that's the whole point of stupid simple. You know, YouTube projects live and die by the audience reaction. The numbers for this project are better than average, so that tells me some people are interested in the project. Now, despite having almost 200,000 subscribers, this channel doesn't earn a lot of revenue. For example, part 1 of this series generated $600. Part 2 generated $450. You know, the Chevy S10 videos don't do so well. I love doing all the projects, but at the same time I have to keep the revenue flowing to continue operations. The best way to support this channel is to subscribe. Subscribing's free to you, so it's a win-win. Anyway, we had excellent results with the stupid simple fuel injection project today, and I'm very happy with the progress so far. For the folks who are interested in the code and the more technical aspects of this project, stick around till after the credits roll and we'll go in for a deep dive. Well, that's all I have for today, and we'll see you next time. Until then. Welcome back, I guess. This is kind of the nerd after party, and the nerds know what I'm talking about. Anyway, the code is way too big to go through line by line, so I put a link to it and you can grab it at the GitHub website. You can download the code from there, and I also put the STL files for the 3D printed parts that I used in this project. You know, I make YouTube videos and I share my stuff. However, I'm unable to do tech support. So if you fool around with this stuff, you're pretty much on your own. Now, this was a lot of code to write in 24 hours. In the video that you just saw, that was basically the first time the engine ran after the final tuning of the field table. So from nothing to a running engine took 24 hours. Actually, a lot less, more like 16 hours. Anyway, doing a project like this, there's going to be many hardware and software conflicts, and I had to use ChatGPT to sort out any potential problems. Now, I didn't tell Chat that I was doing a fuel injection project. Nope, that was my little secret for the moment. Basically, I had Chat rewrite my code so the RPM data collection and the fixed frequency variable duty cycle code could exist in the same space and operate independently of each other. The last I checked, the RPM stuff was 52 lines of code, and that stuff's not easy to do and have a very fast update. Anyway, once the basic code was written, I tested it on the engine with the carburetor installed. This way I could sort out any of the problems with noise on the crank sensor input. Once I was able to eliminate all the bugs and get solid RPM data, then I laced a bunch of my code on top of Chat's code. Now, the trick that I used was, you see, everything I wrote that I absolutely did not want to change, I identified with this label. That way, Chat recognized that it didn't have authority to change those lines of code. At that point in the project, I installed the fuel injection system and I was able to run the engine with manual injector control, and that was to collect RPM and MAP data at various engine speeds and loads. It was just handwritten notes with my observations, but it was very tedious. Once I had the data, I uploaded my hodgepodge code back to Chat. I explained what I was doing and I gave it the rule that it wasn't allowed to change any code that was marked with this. You know, Chat's not a real person, but it hated the brute force code that I wrote. It totally despised it. Now, here's the problem with AI. It knows way too much. And when it analyzed my fuel injection plan, it wasn't happy, but it understood it. Chat understood why I was using brute force, and Chat admitted that this didn't use valuable resources. So Chat accepted the brute force method, but it indicated that it needs to be changed at some point. I don't recall how many steps it took, but it was no more than 5 versions of the code. At each step, I gave Chat a problem to solve, and it came back with a solution. And that solution was immediately tested on the engine. Doing this in baby steps was the right approach because it simplified debugging. Now, with Chat's help, a proper fuel table was constructed, and by the end of the day, I had a fully functional, very simple speed density throttle body fuel injection system. You know, the funny part is, at that point, Chat embraced the brute force method to collect map data, and it said it was very clever. Now, the code is not perfect, and it's somewhat awkward. You see, the constraints that I put on Chat with the rule not to modify code marked with this turned out to be problematic in some cases. So, Chat wrote around the areas where it wasn't able to modify my code. A perfect example is right here. This 1200 was a number for the brute force sample rate, so the code is still there, but Chat did a bit of magic to work around it. Now, it did occur to me to give Chat unrestricted access and have it rewrite the final version. But no, I think I'm going to keep the human part of this project less than perfect because after all, I am human. The code was a big part of this project. Now, I don't believe Chat could have written something this stupid because, well, all the rules about fuel injection were broken. I reckon Chat would have made the right choices and not taken any shortcuts, and in my opinion, that code probably wouldn't work. You see, Chat is book smart, but it doesn't have practical skills with hands-on experience. I've read the books and I've worked on cars that ran okay but had massive problems with the fuel injection system. And I've also tuned EFI systems from scratch. Along the way, you sort of get an idea how sloppy a system can be and still work. Anyway, if someone's interested in the actual code and how to use it, here are a few tips. This section is for the adapted map sampling, and these are the variables that can be changed to whatever you want. On a single cylinder engine, this works great as is, and it doesn't affect the performance in a negative way. Right here are the variables where the Arduino will take over. At 600 RPM, the fuel injection is active, and at 400 RPMs, the fuel injection turns off. This bit of code assumes the engine was primed for starting, and the engine will run for a few moments on raw gasoline. This bit of code takes care of the noise that may be present on the crank sensor input. I have it set to 4,000 and it can go up to 6,000, possibly higher. But if you have to go beyond 6,000, then it's time for a second look at the wiring because you're getting way too much noise on the line. This is the prime button code. This is very sloppy and it's blocking code. If the prime button is pushed while the engine's running, well, you're going to get a squirt of raw gasoline, which may be helpful depending on the circumstances. However, while this bit of code is active, nothing else in the EI system will work. This code takes priority. It's sloppy, but it has a purpose. This line here is for the manual fuel trim. Right now it's set to plus minus 35, but it can be modified to anything you want. For instance, if you change it from 35 to 300, you get a bigger change in the fuel trim. So if for some reason the engine's running very lean throughout the range, adjusting this knob for more fuel will fix that temporarily. Now, with the addition of some clever code, this could be used as a gateway to modify the air-fuel mixture with a wideband oxygen sensor. That may or may not be true. I haven't tested this idea, but provisions for fuel trim was not accidental. And finally, the debug section. This will spit out data every 2,000 loops of the program. Now, this stuff is harmless and it doesn't affect the timing of the system, or at least it shouldn't. Now, nothing in this fuel injection system is synchronized. It processes the data whenever it shows up and the injector duty cycle is modified if required. It's a very lazy system, but it's tolerant of a lot of extra crap, which works out to be perfect for our stupid simple system. Now, this is the simplified schematic. The power and grounds for everything is assumed. If you can't figure out what's going on here, you might not be ready for a project like this. I'll say this though, the other side of the prime button and the run switch are tied to ground. The MAP sensor we ended up using can measure both vacuum and pressure. The vacuum side of the sensor is low resolution and the full range of the vacuum signal is 350 counts. It's hard to say, but I think the low resolution worked out in our favor. Anyway, the sensor has 6 pins, but don't let that scare you. Only 3 of the pins are used: power, ground, and signal. The rest of the pins are no connects. As I recall, the datasheet for this device shows this thing upside down and it's a bit confusing. When looking at the device, these are the 3 pins you need to deal with: power, which is 5 volts, ground, and signal. The MAP sensor needs to be located above the engine so raw fuel doesn't enter the vacuum line. Well, that's about it for the Nerd Convention today. Hopefully we get good numbers on this video because I really enjoyed this project and I would love to take it to the next level. We'll see you next time. Until then.